All right, today we're going to be working on finding area. Please refer to the notes that I have downloaded online and follow along with them while you're listening to and watching this PowerPoint. I'm not going to read everything to you because I think you can probably do that for yourself, so I'm just going to get started right away. The sigma notation that's referred to is something that you probably encountered in pre-calculus. And the sigma notation uses the Greek letter sigma, capital sigma that is, with a variable called the index of summation, which I'm going to use I in this particular example. Other letters that are sometimes used for that are J and K and N. And I'm going to start with I equal to 1, which is a pretty standard starting point. It's not necessary that you start with 1, but in this context we will, because that implies the first rectangle that we'll be doing. We will see examples with sigma notation with I starting at different places, but for this particular application, we're probably going to see I starting with 1 every time. And then the upper limit of this, the upper bound of this summation is some number. Here I've represented that number with n. Following the sigma is going to be some formula as a function of your index. So for example, I squared being that function or that formula means that you first substitute 1 into your formula plus, then put 2 into your formula, plus, so summation means a sum, and so what we're doing is summing for every integer starting at I equals 1 in this case to n. Now if you're going to have a continuation of a pattern, we use ellipses, these 3 dots, to indicate keep going in the same pattern, and then we'll pick up again either at the end or later on in the series of terms that are added. So I'm going to end this with substitution of n squared, n into the formula, making that n squared. So if you look at example A, for a very specific example, this is kind of a generic one we just looked at, we're doing the sum from I equals 1 to 6 of the formula I. And so we're going to have 1 plus 2 plus 3 plus 4 plus 5, and we keep going until we get to the number on top of the sigma, 6, substitute it in, and we are done. Now this can be simplified. What I'm doing here is just showing how the sigma notation expands. We could do the arithmetic, of course, and simplify this to be, let's see, 6, 10, 21. That took me a long time, didn't it? Sorry about that. Okay, the next example. Sigma starting at 0 this time, which I said, remember, the index can start at anything. We will see it in this context after we finish these examples. Starting at 1, we're going to start with other things in these first examples. Okay, the formula this time is I plus 1. So substituting in first 0, plus, now put in 1, now put in 2, now put in 3, now put in 4, and finally put in 5. So that expands this one. If we simplify, that becomes 1 plus 2 plus 3 plus 4 plus 5 plus 6. Interestingly enough, you'll notice that this example in part B ended up giving us the exact same numbers that we found in A. So a different formula and a different starting point. That's how you can have infinitely many different sigma notations to express a given sum. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 can be represented with the version in A or the version in B getting this exact same result. So that means, of course, that there's not a uniqueness to these sigma notations. They have a unique result, but when we reverse this and rewrite a sum in sigma notation, there's not always just one correct answer. I will say, however, that generally speaking, there is one that's considered the simplest. Okay. So, next one. We're starting with J, this time as the index, starting with a value of 3, and we're going to 7. So, of course, that means substitute in 3 to our formula. Oops, I see that I just messed up, so let me back up. I forgot to write the formula behind the sigma. I don't know if you can hear my dog barking, but he's sort of distracting me, which is unfortunate. Okay, so this is J squared. So, starting with 3, 3 squared, plus 4 squared, plus 5 squared, plus 6 squared, plus 7 squared. I'm not necessarily going to simplify every time because I think you probably get the idea of how that works. So you can simplify these if you care to, but I'm not going to, in this case, necessarily simplify. All right, so I move this down. I'm going to start the next part of this, which is part D. The formula is sigma with an index of j, starting with a lower bound of 1 and an upper bound of 5. The formula this time is 1 divided by the square root of j. So this is 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3, etc. And of course this is simplifiable. I'm just writing out the basic initial step of substitution. And then of course if we wanted to simplify these, we certainly could. As I said earlier, I'm not interested necessarily in simplifying all of them. All right, E. For E, we're going from k equals 1 to n, and our formula is 1 over n times k squared plus 1. All right, so in this example we get 1 over n times 1 squared plus 1 plus 1 over n 2 squared plus 1 plus 1 over n 3 squared plus 1, etc., plus dot dot dot, plus 1 over n times the quantity n squared plus 1. Oops, that doesn't look very pretty over there. Sorry about that. I'm not going to worry about going back and fixing every little thing here. Hopefully you can tell that I meant to write n squared plus 1 before I got a little bit distracted by the edge of the screen. Right now I'm trying to figure out a good way to move this down. Last time I thought it was a little bit slow. Let me see if I can increase the speed. That's a little bit better. Okay. Okay, so F. Sigma I equals 1 to n of f of x sub I delta x. So this is f of x sub 1 times delta x plus f of x sub 2 times delta x plus f of x sub 3. You might notice that I'm generally using at least 3 versions of the first few substitutions to establish a pattern. And once the pattern is clearly established, usually 3 or 4 terms is enough, then I'm going to use the ellipses plus dot dot dot, and then my final one will be f of x sub n times delta x. Notice that the formulas in the last two, there were other things in the formula, like the n in part E, or the f of something and delta x, and those stayed constant. So the only changing thing is the index variable k in example E and I in example F. Everything else stays the same. All right. So interestingly enough, if we look back at E for just a moment, if I had room, I'd go back up there and do this. But you might notice that for E, there is a common factor of 1 over n, which if I were to factor that out, and of course I could have written this in simplified form, but I think you'll understand why in just a second why I chose not to. What I'm getting are all of the terms that result after I factored out the common 1 over n. I'll get a chance to make this n squared plus 1 from above look a whole lot better. And then that 1 over n could be multiplied by sigma, and this is the first chance we have to go backwards, of a new formula. Let's stick with k, it won't hurt anything. 1 would be the first thing we put in to mimic what we saw before, to n. And this formula would be k squared plus 1. So notice that the 1 over n, if you look at the beginning of part E and where I just ended, it's as if that 1 over n is a constant and it can come out in front of the sigma. And in fact, that's one of the properties of summation. That we could derive these using the properties of commutativity and associativity and the distributive property of addition over multiplication, and get the formulas that I'm trying to indicate, like part E, that 1 over n is treated like a constant and it can be pulled out in front. And that's our first property, number 1 being, of course, sigma of I equals 1 to n. Does not have to start with 1, but we're writing it that way to mimic where we'll be going soon. That k is not really part of the a sub I formula, and so it can be brought out in front of the sigma like that. And it would not be that hard to prove. We just use generic formulas and it would look a lot like what I extended part E above. How I did that, it would look a lot like that. So we're not going to prove these, I'm just saying they could be proved. The next property is sigma from I equals 1 to n of the sum of two formulas, or the difference of two formulas. Turns out to be the sum of the first formula plus or minus the sum of the second formula. Notice that when you do that, you have to keep your index and lower and upper bounds the same. Excuse me, I'm going to have to pick up my phone. 1 minute, I will be back.